Smart internet-connected devices have become very prevalent, and it's almost impossible to avoid them. Even if you don't buy voluntary surveillance devices like voice assistants and cameras that work through the cloud, it seems like every light bulb, every thermostat, and every household appliance has its own app and wants to extort you for your Wi-Fi password. And who knows what happens once they get it. Being on the Wi-Fi doesn't just grant access to the internet, it also grants access to your whole LAN. Hopefully the situation will improve in the future, maybe thanks to standards like Matter and Thread. But in this video, we will explore how we can deal with the Wi-Fi connected smart devices. Perhaps we can put them in a little networking prison and make them suffer. Or at least we can create some separation between IoT and LAN devices with virtual Wi-Fi interfaces and VLANs. And then we can use firewall rules and queues to keep our home network safe and reliable. For this demonstration, I've already pre-configured this hex-s and this HAP-AX² to simulate a realistic network. The hex-s has a trunk port with both VLANs that we will use, and the HAP-AX² is just going to show us how the network looks from the perspective of an IoT device. So neither of them is a necessity. The whole configuration that you will see is happening on a single access point. What I have here is a HAP-AX running the default configuration. So far, I've only changed the identity name so it is easier to tell them apart. The first thing that we're going to need is a 2.4 GHz Wi-Fi interface. You could repurpose an existing interface solely for IoT, but you don't have to, because the route trace lets you create multiple virtual Wi-Fi interfaces. There are hardware and physics limitations, of course, so you couldn't just create a million of them. The way that virtual interfaces work is that you take the radio, the Wi-Fi hardware that emits wireless signals, and have it advertise more than one SSID. The main upside is that these new Wi-Fi networks can then have very specific security configurations, but the downside is that it all happens on the same physical medium. So you can't just have the virtual interface operate at a different frequency than its parent or master interface, for example. And also, the hardware resources are limited, so overall, the more virtual interfaces you add, the slower they will get on average. If you are curious about the maximum limit for your access point, just type in the terminal interface Wi-Fi radio print detail and look for max interfaces. But let's get on with the configuration. First, you'll want to find the 2.4 GHz interface on your AP. For mine, that will be Wi-Fi 1, and we can verify this in the Channel tab. You will notice later that this does not exist for virtual interfaces. Now, in the security settings, the IoT devices will most likely need WPA2 for compatibility. But if you're only using this as a parent interface, you can safely disable it and stick to the WPA3 for your more important devices. To add a virtual Wi-Fi interface, simply click New and select Wi-Fi. In the security settings, select the authentication types you need and enter the passphrase you want to use. In the Configuration tab, enter your chosen SSID. In the General tab, you can specify an easy-to-remember name, and of course, if you ever need a station instead of an access point, you could simply change it in the mode at the bottom. Click OK to complete. An optional crazy thing you could do to make your Wi-Fi security ridiculous would be to give each station a unique passphrase and isolate them from other devices, so that if one got compromised, the bad things it could do would be very limited. Personally, I would not bother doing this in a home setup, but just to entertain the thought. If you go to Interface Wi-Fi Access List, you will find that you can add rules. They can be used to filter Wi-Fi devices by various properties, but most importantly, the MAC address. And then you can give them specific treatment, such as request a unique passphrase. Notice the created rule is an accept action, similar to firewall rules. So you could add a reject rule in the end, limiting access to very specific devices. Other interesting things you could do are client isolation, which prevents a device from talking to other Wi-Fi connected devices, or you could even override VLAN configuration and assign a specific ID. Then there's another interesting configuration option that I don't need right now, but I should mention it in case you're using CAPsMAN. Datapath settings can be found under each Wi-Fi interface. Notice you could assign a bridge, perform client isolation, and assign a VLAN ID among other things. All those settings can be found elsewhere, but in this tab, they are meant to be applied dynamically. This is necessary when using CAPsMAN, as it applies Wi-Fi configuration to other devices. The managed interfaces on those devices are essentially created at runtime, and that means you cannot include them in your static configuration. So in a nutshell, if you're running a CAPsMAN controller, you will need to turn your dynamic IoT interface into an access port from the Datapath section. Now, I'm only setting up a single access point here, so I don't need to worry about dynamically created interfaces, so I will proceed with a static VLAN configuration. But before that, we need to understand what happens with any new interfaces that are created on top of the default configuration. The interface list section in the default configuration contains a LAN list and a WAN list. Typically, you have a single WAN port, and then the LAN is a pre-configured bridge with all of its ports. This allows for simplified configurations elsewhere, especially in the firewall. But notice the newly created Wi-Fi IoT interface is in neither LAN nor WAN. Security-wise, it is in a gray zone, and you will probably want to either add it to the LAN interface list or add it as a port to your bridge. I will address that in a moment. There might be cases where you want an interface that is in neither the LAN list nor the LAN bridge. Then you might need to adjust your firewall. The forward chain should not cause any issues, but the input chain has a drop rule that would prevent any non-LAN ports from login attempts into the router, and it could block other router-OS features from working as expected. A tempting option would be to simply change the not LAN interface list to WAN, but this is far from ideal, and in our case, we actually want to block our IoT devices from interacting with our router too much, so I will leave this rule as it was and later make a surgical exception for mDNS input. For our setup, we need to create a couple more interfaces for our VLANs. Let's say we want to use VLAN 10 for our LAN network and we want our IoT devices in VLAN 20. Note that we are creating these interfaces on top of our bridge, but they are not bridge ports, so currently they do not belong to the LAN. On our bridge, we add our IoT Wi-Fi port with PBID 20, and we will also set the frame types to untagged. This creates an interesting situation where the Wi-Fi interface is in our LAN, but any incoming traffic will get immediately put into VLAN 20, where it is no longer part of LAN. Next, you'll want to configure any additional access ports for VLAN 10 and VLAN 20. Most ports will probably go into VLAN 10. Then in my setup, Ether 4 will be a trunk port, so I don't need to set its PVID, but I do want to change the frame type from all to VLAN tagged only. To complete the trunk port, we need to go to the VLANs tab on the bridge and add VLAN 10 tagged port Ether 4 and then VLAN 20 tagged port Ether 4. Now before we turn on VLAN filtering, we need to make sure our VLAN 10 traffic is part of the LAN and we do not lose access to our device. We will accomplish this by simply adding the VLAN 10 LAN interface to our LAN interface list. After that, we can go to the Bridge Settings VLAN tab and check the VLAN filtering. When you hit OK, you will lose the connection to your device and you will need to reconnect using the MAC address and fix the IP configuration. If you open up the addresses and the DHCP server, you will see that there is now a problem. You need to update the LAN addresses interface from the bridge to the VLAN 10 LAN interface and then do the same with the DHCP server interface. After that, we want to add an IP address for our VLAN 20 interface and run the DHCP setup for it, so that our IoT devices can also receive addresses through DHCP. Then before we move on to the firewall setup, you'll most likely want to enable the mDNS repeater in the DNS settings. For it to actually work with the default firewall, you will need to do a tweak in a second. Now, when it comes to firewall, it is important to understand that you actually have two of them. If you are running IPv6 in your network, you will have to take any adjustments that we make to the IP version 4 firewall and repeat them in the IPv6 firewall. Even if you are not distributing IPv6 addresses in your network, every interface still gets a link local IPv6 address, and those link local addresses can theoretically be used to bypass IPv4 firewall rules to some extent. But don't worry, if you're not sure what you're doing with IPv6, you have an easy out. You can simply open IPv6 settings and disable IPv6. In the IPv4 firewall, let's look at the input chain. Remember, there's this rule at the bottom that drops everything not coming from LAN. For the mDNS repeater to work correctly with your default firewall, you might have to add an input firewall rule that accepts mDNS traffic, as any packets that will get repeated are first considered as input to the router. Filter for UDP traffic coming from port 5353 and only the specific interface you need to avoid unnecessary security holes in places like your WAN interface. The default firewall contains this accept rule for ICMP, and it just makes your device pingable from all interfaces, including WAN and any new interfaces you create. This is pretty much harmless, but it does make your router's IP addresses discoverable from any of its interfaces. But you might not want your light bulb to be able to find out your WAN address by performing a simple network scan, for example. So we might as well modify the ICMP rule and set the in interface to be LAN exclusively. This way, any pings coming from the IoT network or the internet are simply rejected. Now in the forward chain, we need to prevent IoT devices from messing with things in the rest of our LAN. We can add a simple rule that filters for connections coming from the IoT VLAN going to the LAN. And we should select only the connection state new, as we want our LAN devices to be able to establish connections to IoT, but not vice versa. Just move this drop rule to the top of your forward chain. In the setup that I'm going for in this demonstration, I do not need any more forwarding rules, but if we had more VLANs or a guest Wi-Fi interface, for example, then we would need more. You would want another drop rule preventing IoT devices from opening new connections to your guest network. And you would also want 2 more drop rules restricting the guests from opening connections to the LAN and IoT networks as well. You can create all those rules in the same fashion as the drop rule we just added. Then you might also be interested in completely preventing the IoT VLAN from accessing the internet. I suppose it is removing the I in the IoT, but in some situations that makes sense. You could do this by adding another drop rule with in interface set to your IoT VLAN and out interface list set to the WAN list. Okay, most likely you do not want to cut off internet access from your IoT network, but you want to make sure that your IoT devices can never hog up all of your bandwidth. To set up rate limiting using the queue-tree method, you'll want to first open Mangle rules and mark packets in both traffic directions. For downloads, select the forward chain and in the in-out interfaces specify traffic coming from not your interface going to it. Then for uploads, you will want to do the opposite. Mark traffic coming from the interface and going anywhere else. Then make sure you have disabled fast track. Finally, in queue-tree, add global queue and give it a child queue using the download packet mark and set max limit. Do the same for uploads and you're set. Now let's test our setup from the perspective of these other 2 devices. On the HAP-AX², if we try to ping the LAN address of our AP, it fails. And if we switch to the IoT address, it also fails because we are only allowing incoming pings from LAN devices. If we switch to an IP address from another device in the IoT network, we do get a response as expected. And then in neighbors, we can see that there are 2 other routerless devices. But let's run a bandwidth test to a server that's behind our AP's WAN port. Within a couple of seconds, we can see that it finds our throughput to be around 20 megabits per second, which is what it should be. Now let's see about the hex. It has IP addresses in both VLANs, and currently it is set up to route the bandwidth test through the IoT VLAN. So if we run the test, it will have the same throughput as on the HAP-AX². Do know that the limitation we put in place is for the whole VLAN, so multiple devices won't be able to achieve this throughput at the same time. If we switch to a route through the LAN, we can achieve speeds that are much greater than the IoT rate limits, although we are not reaching the top performance of the hex-S, because the bandwidth test itself is taxing the CPU. This completes this configuration guide. You should be able to use your new setup safely with your IoT devices. And on top of that, if you need to run some sort of home server that interacts with the IoT network, you can make that happen with the container and apps features directly on your access point. My only advice would be to put them in the LAN network and not together with IoT, so that the firewall is protecting your containerized server against login attempts from IoT devices.